I would like to give an introduction to the OFDM and OFDMA tutorial. This will basically be an introduction and a short overview. We won't go in depth in any particular subject, but the purpose is to give you a general idea about the tutorial, especially provided that it is more than 16 hours long, and at least you can get an idea of what to expect. As we know, satellite digital multimedia broadcasting systems are one of the prime areas that OFDM has been applied to, and we expect to see OFDM-based satellite digital multimedia broadcasting systems deployed in the future, DMB for short. We're also seeing OFDM and OFDMA in particular being proposed for 4G systems. So there is a great interest in both OFDM and OFDMA in emerging wireless technologies. One of the big new growing areas, of course, is WiMAX, in which you can deploy broadband wireless communications in fixed wireless networks in places where they lack infrastructure or in ad hoc situations. And that is, of course, a growing area, and we will cover both OFDM and OFDMA and WiMAX and IEEE 802.16-2004. WiMAX is also being used in built-up areas, especially since as the capacity for broadband communications over wireless networks is increasing with the advances in technology both in OFDM and OFDMA and in coding techniques, we can easily take advantage of the higher capacities even in built-up areas. Here we're just showing, for example, a fixed wireless network within a urban environment, which is again easily deployed and taking advantage of the advances in capacity. For example, we're looking at data rates of 1 gigabits per second in fixed wireless access networks and over 100 megabits per second in mobile wireless access networks. OFDMA technology is also a foundation for mobile wireless access, especially with the announcement and the publication in 2005 of the IEEE 802.16e standard, and we will go in detail over the mobile wireless access technologies, especially OFDMA. We will also talk about scalable OFDMA. We will cover, for example, the Doppler spread, the power spectral density due to Doppler and vehicle motion and how it impacts the performance. And we will go in detail in general on OFDMA as applied to mobile wireless access networks. And this is a growing area. There's also a lot of advances being made in smart antennas and especially in MIMO and in beamforming, and those are topics for future tutorials. One major aspect of moving to OFDM and OFDMA technologies is the fact that we don't need to have line-of-sight communications. For example, previously when you had single carrier system, even in the original 802.16 and also in 802.16a, the single carrier systems needed line of sight, but with OFDM and OFDMA we can achieve communications with non-line of sight situations, which is a big plus in the deployment of fixed wireless access networks and also mobile wireless access networks. And we'll go over all the issues involved with non-line of sight communications. We will use IEEE 802.11a and the implementation of OFDM and IEEE 802.11a and an end-to-end implementation in order to describe in detail the implementation of an OFDM system. And in this way we will be able to describe in detail how OFDM systems are built from the ground up and also on a block-by-block basis. Using IEEE 802.11a as a basis, we lay the foundations for a deeper understanding of OFDM and OFDMA in IEEE 802.16-2004 and IEEE 802.16-2005. The original paper on OFDM was published in 1971, Data Transmission by Frequency Division Multiplexing using the discrete Fourier transform, and this was a big breakthrough, especially since the discrete Fourier transform could be implemented using a fast Fourier transform. Another very important paper is this paper published in 1989. In this paper, the cyclic prefix was introduced. The cyclic prefix allows for simple equalization using zero forcing in the frequency domain, since the cyclic prefix essentially gets rid of intersymbol interference that destroys orthogonality between the carriers in OFDM. So this was a very important paper in the development of OFDM. We will begin by discussing multipath fading channels and the challenges that they impose in terms of high capacity, reliable wireless communications over multipath fading channels. For example, here we're showing the fading characteristics of a 20 megahertz channel with a 150 nanosecond RMS delay spread, and as we can see, we have deep fades in which portions of the spectrum operate at very low signal to noise ratio. At the bottom we're showing the power delay profile for the channel whose frequency response we show at the top. So initially we will introduce you to all the issues involved with multipath fading channels and how to model them and what are the specifications used in order to characterize multipath fading channels. We will also discuss ways for combating multipath fading channels, in particular by breaking the bandwidth into multiple sub-channels, each with a narrow bandwidth, so that for each sub-channel we have flat fading versus frequency selective fading, and how we would multiplex all the data that is transmitted in parallel, and then we will derive a bandwidth efficient technology for transmitting over multipath fading channels, in particular orthogonal frequency division multiplex. Before we get into OFDM, we have a self-contained tutorial on baseband digital communication links, both bandpass and baseband, and we will go over the basics of communications over digital links. For example, here we show a baseband digital communication link. We will discuss how to transmit digital data over band-limited channels. We will talk about Nyquist pulse shaping. We'll talk about match filtering, and we will actually derive the probability of error versus signal-to-noise ratio. We'll go over the details and the trade-offs in terms of bandwidth versus signaling rate, and we'll talk about eye diagrams, Nyquist pulse shaping, and parameters that are needed in order to transmit over band-limited channels. We will also talk about ways to fight intersymbol interference. In particular, we will go over details of derivation of quadrature modulation and demodulation and all the math behind bandpass communications, but these are all optional material. A major part of this tutorial is the fundamentals of OFDM, and we will go into detail on OFDM and how OFDM is used in order to provide reliable and robust communications over multipath fading channels. We will describe how OFDM achieves spectral efficiency and the orthogonality between the carriers, and we will actually derive the discrete Fourier transform formulation of OFDM, and we'll also discuss the FFT as used in, for example, the demodulation and the inverse FFT for the modulation of OFDM signals. In particular, when you're dealing with multipath fading channels, we have to deal with intersymbol interference, and we will discuss the mechanisms for intersymbol interference and ways to combat intersymbol interference both through time domain and frequency domain equalization. For the case of OFDM is the fact that we can use the cyclic prefix in order to combat intersymbol interference in the channel, and we will go over the use of the cyclic prefix in order to combat intersymbol interference, and also the parameters involved and the relationship of the cyclic prefix to intersymbol interference in terms of the RMS delay spread of the channel and other parameters. We will also show how the cyclic prefix provides a tolerance for timing synchronization in acquisition, and we will also see the impact of cyclic prefix on the throughput of the system. We will also cover the topic of frequency domain equalization in OFDM systems. Basically here we're showing the estimated channel at the receiver and the constellation before equalization and the constellation after equalization. Here we show the block diagram for an 802.11a OFDM based wireless communication system. We're showing the transmitter on the top and the receiver on the bottom. During the tutorial we will go over each block in detail. For example, we will discuss the convolution encoder, which provides forward error correction coding with a Viterbi decoder. We will talk about puncturing, which allows us to achieve high throughput in cases where we have high signal-to-noise ratio by trading off redundancy for throughput. We will talk about the interleaver, which combined with forward error correction coding provides for a robust, reliable communication link over wireless communication channels with OFDM. There are many issues involved with OFDM, in particular the arrangement of the data carriers, the pilots, the guard intervals, and we'll talk about that. Here we're showing the inverse FFT, which is used to modulate OFDM carriers. Here we add the cyclic prefix, we do a parallel to serial conversion, and we convert the signals, the N-phase and quadrature, from digital to analog. We will talk in detail about the RF transmitter and the RF receiver. In particular, we would focus on direct conversion transmitter and a direct conversion receiver. At the receiver, we have the acquisition blocks. We will go into detail in the acquisition blocks. Initially, we will assume perfect acquisition and talk about the steady state OFDM demodulation. In this case, we're showing the FFT, which demodulates OFDM time domain signals into frequency domain carriers. We're actually equalizing the carriers on a per carrier basis. We do a demapping from the constellation points into soft bits. We do a deinterleaving, a depuncture. We do a Viterbi decoding and a descrambler, recover the originally transmitted data. So in this tutorial, we will go over every single block in this block diagram, and you will have a comprehensive understanding of the functions of each particular block and its role in the overall system. Here, for example, we're showing the convolutional encoder. We'll go over in detail how the convolutional encoder works. We have a whole section on the operation of the Viterbi decoder, its architecture, and the basic design parameters and trade-offs in its implementation. The material is arranged in a way that, for example, the in-depth coverage of the Viterbi decoder is optional, but all the material is there in order for you to achieve a good understanding of how the Viterbi decoder works and how convolutional encoder combined with the Viterbi decoder provides higher reliability in terms of forward error correction coding. We'll go over puncturing in detail. Puncturing basically allows us to trade off redundancy in the forward error correcting coding with higher bandwidths in cases where we have high signal to noise ratios. So for example, if we have a high signal to noise ratio, then we don't have to use all the redundancy in the convolutional encoder. We can actually employ puncturing where we get rid of redundant bits, and we will show how that improves the throughput so we can take advantage of cases where we have high signal to noise ratio in order to achieve higher throughput while at the same time having forward error correction coding. Interleaving and deinterleaving combined with forward error correction coding is very important in terms of preventing bursty errors when you have deep fades in which multiple carriers can be wiped out or are received with low SNR and you have low reliability in the bits. With interleaving and deinterleaving, we basically take bursty errors that might happen in the case that we don't have interleaving and interleaving. But with interleaving and deinterleaving, we actually take those bursty errors and make them such that they appear as random errors at the input of the Viterbi decoder, and the Viterbi decoder is quite capable of correcting for those random bit errors, but not very good at correcting for bursty errors. So interleaving and deinterleaving are integral to OFDM, especially in IEEE 802.11a and in IEEE 802.16-2004 and 2005. In terms of combining interleaving with forward error correction coding to achieve robust, reliable communications over wireless channels. We will discuss the RF transmitter, especially the direct conversion architecture, in detail. We will go over the impact of nonlinearities in the PA on the overall performance and talk about all the parameters you need to know about in terms of specifying the PA in order to meet design objectives. We'll also talk about IQ imbalance and other issues involved in the implementation of direct conversion RF transmitters. We will discuss in detail the direct conversion receiver, in which we take the channel of interest and demodulate that back to baseband in a direct conversion receiver. That, of course, has many advantages and disadvantages, which we'll go over all of them in detail. In particular, with direct conversion receivers, we have issues in terms of DC offset, in terms of IQ imbalance, and other issues that we'll deal with. In particular, we're going to talk about automatic gain control, since AGC is a key issue in the design of OFDM systems, where we have a very tight interaction between the baseband digital demodulator and the RF analog front end. AGC is very important, in particular to reduce the requirements on the dynamic range of the analog to digital converters, and also to actually achieve good performance over a wide dynamic range and reduce the requirements on some of the key components in the analog front end. So we'll talk about AGC in detail and show how the preamble is processed during initial acquisition in order to achieve AGC, and what are the interactions between the digital baseband demodulator and the RF front end is in terms of controlling the gains on the analog front end and peeling off gains for high signal to noise ratio signals, and at the same time achieving the highest sensitivity for the cases where we have low signal to noise ratio. Throughout the tutorial, we will discuss the effects of multipath fading channel on the performance of the receiver, and here we're basically showing some of the issues involved with AGC dealing with multipath fading channels, where we show how much margin you have to allow for the case where you have multipath fading channels with large RMS delay spreads. And we'll discuss the impact of multipath fading channels throughout the discussion of acquisition systems. A key component of a OFDM system is the estimation and correction for the carrier offset frequency between the transmitter and receiver, because if there is any carrier offset frequency between the transmitter and receiver, then the OFDM carriers lose orthogonality and you have inter-carrier interference. We will go in detail into the derivation of an algorithm for the estimation of the carrier offset frequency and how to eliminate it. For example, here we're showing a case where we have 1 kHz of residual carrier offset, and we're showing its estimation and correction over here where we recover the original constellation. So we devote quite a bit of time on carrier frequency offset estimation and correction algorithms and their implementation. We have a major section on acquisition, and in particular on packet detection and coarse timing synchronization in OFDM systems using 802.11a as an example. This material is also very useful in terms of implementations of any OFDM system, in particular 802.16-2004 and -2005 systems, and orthogonal frequency division multiplexing systems used in other wireless networks. For example, here we're showing two methods for packet detection, one based on autocorrelation and one based on cross-correlation. We show the advantages and disadvantages of each method, and in particular we analyze their performance with multipath fading channels, and we show where one method is more powerful than the other and where the trade-offs are. So we have a detailed description of packet detection and acquisition based on processing of the preamble in OFDM, using 802.11a as an example. Another issue that we deal with is adjacent channel interference. For example, here we're showing the desired channel and an adjacent channel, in which the adjacent channel is transmitted with a higher power than our desired channel, and we will talk about the issues involved in combating jammers and interference in OFDM systems, in particular the trade-offs between filtering in the analog domain and the digital domain, and we'll talk about how to prevent aliasing and so forth. Timing offset is a big issue. In particular, when you transmit an OFDM signal from the transmitter, there is going to be a timing offset between the sampling at the receiver and the actual sampling that was used at the transmitter, and that timing offset causes a deterioration in performance unless we find means for combating it and estimating it and eliminating its effects. So we'll discuss those in detail. In particular, you're always going to have a drift in timing over long packets, and we'll discuss how pilot tracking can actually estimate and correct for timing drift. For example, over here we show a timing offset of 12.5 nanoseconds, and here we show a timing offset of 5 nanoseconds, and we're showing the actual pilots, and we can see how different timing offsets affect the pilots in a different way, and we'll go into detail into how timing offset affects the received constellation and how we can actually estimate for it and correct for it. We have independent sections on OFDM and OFDMA as used in 802.16-2004, and especially with 802.16-2004 where the WiMAX profiles are supported. In this case, we're showing a point-to-multipoint links for fixed wireless networks. First, we will actually discuss the OFDM implementation using a 256-point FFT. One particular block that has been added compared to 802.11a is the Reed-Solomon coder and Reed-Solomon decoder at the transmitter and receiver, which forms the outer code in a concatenated code, with the inner code being the convolutional encoder. And we will discuss that how the Viterbi decoder, for example, when it is unable to correct for bit errors, it does produce a bursty error, and the outer Reed-Solomon coder and decoding process can correct for bursty errors. Also, we may encounter bursty errors in multipath fading channels, in which, again, the Reed-Solomon coder and decoder as the outer code provides a high level of robustness in terms of reliable communications over wireless multipath fading channels. Using IEEE 802.11a as a foundation, we will use that as a basis for our tutorial on the 256-point FFT OFDM-based system in IEEE 802.2004. In particular, we will go over the time division duplex as used in OFDM metropolitan wide area networks. Here, for example, we're showing the TDD frames, and we'll show how each frame is subdivided into a downlink subframe and uplink subframe. Here we're showing, for example, the uplink subframe, in which we have data bursts from individual subscriber stations back to the base station. We'll go over detail into how TDMA in the uplink subframe actually works, and issues involved with synchronization of the subscriber stations and power control, and in particular how we achieve alignment. And also we go over the maps that instruct each individual subscriber as to when to send their data bursts back to the base stations. So there are a lot of issues involved with TDD, with OFDM, and we'll discuss those in detail. We also have a comprehensive tutorial on OFDM multiple access. Here we show the downlink subframe and the uplink subframe in a TDD frame for OFDMA. We will go in detail as to how the carriers in a, for example, 2048-point FFT are arranged into subchannels, and then each data burst is arranged in terms of a subchannel offset, the number of subchannels, a time slot, and number of time slots, which are OFDM symbols, in order to define both downlink bursts and uplink bursts. We'll also go in detail into the initial ranging and what happens in initial registration in order to achieve timing synchronization, where they can transmit in parallel and at the same time achieve timing alignment at the receiver of the base station. There are many issues involved with OFDMA, and we'll go into detail on all those issues, in particular the permutation of the carriers and their arrangement into subchannels. In order to deploy OFDM and OFDMA systems, it is very important to understand the multipath environment and to actually calculate the what we will call the large scale or macro effects like path loss and the effect of terrain on path loss, and also the microscopic effect or small scale effects such as multipath fading and Doppler due to motion. For example, we will present details on path loss models. For example, here we're showing the Stanford University interim model, and this is the macroscopic effect of, that is the path loss from the base station to the subscriber, and we're showing how they depend on terrain, frequency, the base station height, the subscriber height, and other issues. We will derive the Doppler power spectrum in order to characterize mobile environments in which the subscriber is moving at high speeds. For example, here we show the fact that over time the envelope of the received carrier goes through deep fades, and this severely degrades the communication over mobile wireless links, and we'll talk about how to combat this effect, especially with pilot tracking. For example, here we're showing the constellation at the receiver with a vehicle speed at 200 meters per second, but using pilot tracking we're actually able to track the changing channel due to Doppler spread, and we're able to actually correctly demodulate the signal even at speeds of up to 200 meters per second. Doppler is also important in terms of fixed wireless access networks. For example, when you have wind blowing through trees and you have the movement of leaves and so forth, and you have the movement of traffic within built-up urban areas, all these cause the channel to vary, And these are modeled by Doppler fitting, but different than in the case where you have the subscriber moving at high velocities. This is for fixed wireless networks, and we'll discuss how to model these both in terms of software and in general. And finally, we present many areas regarding systems engineering in terms of computing the signal to noise ratio based on the specifications of the, for example, noise figure, bandwidth, bit rates, and so forth, in order so that you can actually design OFDM wireless communication links using 802.11a as a basis, but in particular in order to come up with the requirements to achieve the sensitivity you need in order to meet requirements in terms of range and throughput.